Okay, let's now do several examples of the actual power series. Okay, example number one. Find the radius and the interval of convergence of the series let's say x over 3 to the power n, and determine whether the sum of a series is a continuous function. So let's see what we can do here. First of all, to find the radius and interval of convergence, we have already done that a few sections back. What you need to do is to use either the ratio or the root test. So in this case, probably the root test is going to be easier, right? Because this power series has a form of something to the power n. So use a root test. So what we need to do is to take a limit as n goes to infinity of the nth root of the nth term. So it's absolute value of x over 3 to the n raised to the power 1 over n, right? And the way we apply this test is that we fix x, right, and we send n to infinity. If we're fixing x, then what sort of convergence of a series are we determining, right? As we discussed before, if you fix an x, then you talk about pointwise convergence. So let's just add that here. This guy tests for pointwise convergence. All right, so the only thing that can be negative here is x, actually, right? And then nth power, 1 over nth power, n cancels out, so this is a limit as n approaches infinity of absolute value of x over 3, right? So then the series converges as long as this is less than 1. And so therefore, if x is less than 3, if I multiply both sides by 3, the series converges pointwise. And so therefore, interval of convergence is from minus 3 to 3, and the radius of convergence is 3. One minor caveat here, right? When the limit is equal to 1, right? Then in principle the test is inconclusive, so I have to test the endpoint separately. But in this case, actually something that I did not mention before, but if I look at this series, this is a geometric series, right? And for geometric series, we know that the multiplier has to be less than 1 in absolute value for the series to converge, otherwise it does not converge. And we basically came up with the same conclusion here, so there's no need to test the endpoints. Okay, so the series converges pointwise. How do we answer the second question? Is the sum of a series a continuous function? Well, for one thing, again, because this is a geometric series, I know how to figure out the sum of a series. So it should be 1 over 1 minus x over 3, right? And that seems to be a continuous function when x is between 3 and 3. So in this case, things are simpler. But I don't want to use the knowledge of the sum of a series. Without it, I still want to be able to deduce the same thing. Whether or not the sum of a series is continuous. So again, 1 over 1 minus x over 3 is continuous. I already know it is continuous. In this case, I'm just verifying that my theory works correctly. So number 2. The sum is sum of a series sum of the series is continuous if the sequence of partial sums converges uniformly, right? And we have to specify the interval. Okay, let's do that. In fact, in this case, interval of convergence is from -3 to 3. So if that sequence converges uniformly on -3, 3. Okay, so we need to check if the sequence converges uniformly. So we can either try to verify the M-test, or we can try to prove the Cauchy criterion, uniform Cauchy criterion directly. Or maybe actually there is no uniform convergence. So how to decide? Maybe there is no uniform convergence. How can I test for that? I can test for that by using the test for, you cannot say uniform divergence, but a test that confirms uniform convergence, right? That we proved again in the previous lecture. So how did it go? Let's consider the supremum. X is in -3, 3 of absolute value of fn of x. Remember, if this thing doesn't go to 0 when n goes to infinity, then we cannot have uniform convergence on our interval. Okay, so fine. That is this something that I would be able to compute? Well, let's see. What's fn of x? This is supremum between -3 and 3, open interval, and my function is x over 3 to the power n, right? What is the supremum of this on the interval from -3 to 3? Well, I can get arbitrarily close to 3, right? So for a fixed n, right, my x can be as close to 3 as I wish. So this is, or to -3 for that matter, then this is equal to 3 over 3 to the n, 1. And as n goes to infinity, this does not go to 0, right? So by the test for the lack of uniform convergence, we conclude that the series cannot converge uniformly on -3, 3. And so I cannot really conclude whether or not the sequence, the sum of a series actually is continuous, right? If I can verify Cauchy criterion, then I can prove that the convergence is uniform. If I cannot verify Cauchy criterion, I cannot prove the convergence is uniform, but it doesn't mean that the limit might not be continuous, right? Because what was a theorem that we proved in this regard? If I have a sequence of continuous functions that converges uniformly to another function, then the limiting function must be continuous. But I did, I think, an example or two when I have a sequence of functions that are not, that are continuous and are not convergent uniformly, but they still converge to a continuous function. So what can I do to try to see if maybe I can say something about continuity? So then the idea will be is actually if I look at this computation that I just did, now it checked for uniform convergence of my sequence of partial sums, or it's checked directly for the uniform convergence of absolute values of n on the interval from -3 to 3. And the reason why the uniform convergence is lacking is because when x gets very close to 3, right, then I get 1, and that's a problem. But what if I test a different interval? So instead, let's consider the interval maybe minus a to a, where a is less than 3. A is a positive number, but it's less than 3. Okay? If I consider an interval like that, let's go back here again. So if x is in the interval from -a to a, then I can only, the maximum largest value of x that I can have is going to be a, right? Then I have a over 3 to the power n, and a over 3 to the power n certainly is a number that goes to 0 as n goes to infinity because a is less than 3. Okay, but then this sort of hints that I could maybe compare this to the series of a over 3 to the power n, right? Because the supremum is a over 3 to the power n, and a over 3 to the power n actually itself is a convergent series. So note that x over 3 to the power n is less than a over 3 to the power n if x is between minus a and a, right? Number one. And sum from 0 to infinity of a over 3 to the power n, right? This guy converges. In fact, I don't really need, I don't know why I use a absolute value here. A is a positive number anyhow, so I can replace this just by a over 3 to the power n. Convergence as a geometric series with a multiplier which has absolute value less than 1. Okay, and then what am I concluding from this? So therefore, the series from 0 to infinity of x over 3 to the power n, this converges uniformly on the interval minus a to a by the Weierstrass M test. Okay? Also, x over 3 to the n is continuous in fact everywhere, but in particular on minus a to a for all n greater or equal than 1, right? And this means that the sequence of partial sums in this case is a uniformly convergent sequence of continuous functions. Therefore, we can conclude that the sum of a series of x over n, x over 3 to the n, that this thing is continuous on minus a, right? Not only it is continuous on minus a, but also I selected a in this case randomly, right? A is just some number between 0 and 3. So I can make a as close to 3 as I wish. But that means, so it's continuous on this interval for every a between 0 and 3. And so therefore, the function is continuous on the entire open interval from minus a to a. Right, so even though I don't have uniform convergence on the interval from minus a to a, the sum of the series is still continuous on all points, at all points on the open interval from minus a to a, as we have just proved. let's do one more example. Did I number the previous one? Yes. Same question. Questions for the sum n from 0 to infinity, x to the n divided by n factorial. Let's see what we can do here. Now, I want the interval of convergence, I want the radius of convergence, and I want to see if the sum of a series is a continuous function or not. Now, remember that when I was looking for the interval and the radius of convergence, what did I do first? I used the root test, right, to prove pointwise convergence. And then I had to do something else to prove uniform convergence. If we think about it, actually, if I could prove uniform convergence immediately, then pointwise convergence is a weaker statement. So if a sequence converges uniformly, if a series converges uniformly, it must converge pointwise. So if I can answer the questions for the uniform continuity, for uniform convergence, then I will automatically answer the question for pointwise convergence. So let's see if we can prove a uniform convergence for this series without actually showing pointwise convergence first. And at this point, what do I have? I have a Cauchy criterion, I have Weierstrass m-test. Thinking about the m-test, so for m-test, what do I need? I need to find, so to use the m-test, what do I need? I need to find mn such that find the series mn such that a supremum x in I of absolute value of x to the n over n factorial, that this thing is less than mn for all n, and sum, okay, maybe I should say sequence here, from 1 to infinity, the series of mn's converges, right? So it's bounded, therefore it converges because it's a series of positive numbers. Well, so in advance I didn't tell you what the radius of convergence is, right? Because we decided to go straight to test for uniform convergence. And well, if I didn't tell you what the interval is, then maybe x can be anything. But then there is a problem here, right? Because if I assume that x can be any number, so any number between minus infinity and infinity, then I will run into trouble here because in that case, x to the n over n factorial, when I take a supremum in x, is going to be infinity. So I will not be able to use Weierstrass m-test. In fact, I'm just going to take the supremum is infinity. It doesn't tell me anything. Well, then I can try to utilize what we just did in a previous example, maybe. So let's suppose I cannot test on the interval from minus infinity to infinity, but let's suppose for now that I is equal to, let's limit, our ambition here. So let's make I to be an interval from minus a to a again. And let's say a is just a positive number here. Well, so then, what would I have? Well, certainly in this case, if I take a supremum over x and I of x to the n over n factorial, what do I know? Actually, x can now be any number between minus a and a. X to the n is an increasing function, and its maximum is going to be at a, and we can also use a maximum at minus a because we're taking absolute value. Supremum is a maximum, right, again, because of a closed interval. So this is equal to a to the n divided by n factorial. Okay? All right, so we're looking then at this interval. And then this suggests to us that I can use this number as mn, right? So mn is a to the n over n factorial. Certainly it's a positive number, so I found the upper bound on my sequence of functions. But we need to show now that sum n from 0 to infinity of mn, that this thing converges. Right, and in this case, the only reasonable test to use would be a ratio test. So use the ratio test. What does it tell us? Take a limit as n goes to infinity. Now everything is positive here, so I don't need to take any absolute values. A to the n plus 1 over n plus 1 factorial divided by a to the n over n, right? N plus first term over n factorial. Now, what is n plus 1 factorial? So this is a to the n plus 1 over a to the n. N factorial goes on the top. And my question, what is n plus 1 factorial? It's a product of all integers up to n plus 1. So I can write as, this is n factorial times n plus 1. So then I can cancel a to the n, and I can cancel n factorial. And what's left is a over n plus 1. And of course, what happens to a over n plus 1 for a fixed a as n goes to infinity? This is 0. And 0 clearly is less than 1, right? So mn is indeed converges. Series of mn converges. And therefore, what do I know about my original series? This series converges uniformly on the interval minus a to a. So that's converges uniformly on minus a8. And as a result of that, again, this is continuous always for all n, right? Because you have x to the n divided by n factorial, and it's a number. X to the n power function is always continuous. And so therefore, the sum of the series, our series now, is a series of continuous functions that converges uniformly. So the entire series converges to a continuous function on minus a. In fact, that interval is, I chose it to be closed, so let's keep it closed. Right, and a was chosen arbitrarily, right? A was just an arbitrary positive number. So what I just showed is that the convergence is to a continuous function on minus a for all a greater than 0. But if I have convergence for all a greater than 0, then what can I do with my interval from minus a to a? I can continue growing it without bound in both directions. And so therefore, the series converges to a continuous function everywhere. Right, so if a series converges to a continuous function everywhere, so that means that the interval of convergence is R, and the radius of convergence is infinity. Right, so these are the things that I don't need to compute because I already know them. I can deduce them from the fact that the series converges on the entire real line, right? And one additional question. And that is, does a series from 0 to infinity, does my series of x to the n over n factorial converge uniformly on the entire real line? Well, how do we check? We can try to check again for the test. We can check the test for lack of convergence, because if we have a lack of a uniform convergence, then there is nothing else to do. So what I need to do, I need to compute the supremum. X now is on the entire real line of my absolute value of my function x to the n over n factorial, right? And I'm taking supremum in x while holding n fixed. Well, what is the supremum of x to the n? Right? It doesn't matter what n factorial is, it's just a constant. What's the supremum of x to the n on the entire real line? It's infinity. And so because it's infinity, again, it is not true then that the supremum goes to 0 as k goes to infinity. And so therefore we conclude that the convergence is not uniform. yet again, on every subinterval of R, it is uniform. And because it is uniform on every subinterval, the sum of a series is continuous on every subinterval, so therefore it is continuous everywhere, even though, again, there is no uniform convergence on the entire real line.